Hello, and welcome to video K.4, Relative Velocity. In this video, we will discuss how to solve problems dealing with relative velocities. It corresponds to Chapter 3 in your textbook. Since we've already talked about projectile motion and separating vectors into components, in this video we will essentially be doing the opposite. We'll be combining vectors, in particular velocity vectors, into a resultant vector and seeing what we end up with in terms of where we're standing and what the velocity looks like compared to that perspective. So let's start by reviewing some vector addition rules. First of all, there are multiple methods of combining vectors. If we start with the graphical method, we have the most simple situation where, for example, let's say we have an object that is moving 8 kilometers to the east, and then they continue to move after that, and they go another 6 kilometers. Their total distance moved, their total displacement moved, would be just simply the addition of these two, and we would know that they have a resultant distance of 14 kilometers east. Super simple, and I know you know this. I'm just reminding you of this because we're going to shortly get into two dimensions. Now, if we have another situation where the object starts by moving 8 kilometers to the east and then turns around and moves back 6 kilometers to the west, then in this particular case, the resultant is not going to be the addition of these two, but it's going to be the subtraction of these two. So our resultant would be from where it starts to its end point, and that would be 2 kilometers, again, east. So when we're doing the most basic one-dimensional motion forward or backwards, we are either adding the component vectors or we are subtracting the vectors. Keep in mind that the resultant vector goes from the starting point to the ending point, whether the velocity vectors are in the same direction or not. Okay, we could get a little bit more complicated here as well. We could have something going in two different dimensions. So, for example, we could have, let me set up a set of axes here. West, east, north, south. And we say that the object starts at the origin and it moves east for 10 kilometers, and then they turn and go north for 4 kilometers. We would simply go ahead and graph this as straight lines. Now notice that I have not actually put hash marks on your axes here. You'll be doing these on graph paper, and it would be best for you to go ahead and put the hash marks on so that you are sure that you're drawing things relative to each other, the same amount. That went a bit crazy. In other words, the same sizes. Okay, so we now have our position vector, our distance vector, going east 10 kilometers, then the object turns and goes north 4 kilometers. To find the resultant here, we still want to go from our starting position to our ending position in a straight line because we are looking for our displacement here, not our total distance. So our displacement is simply from our 0 point up to our ending point, and we can call this the resultant displacement, and it is the first vector plus the second vector, where this one would be d1 and this one would be d2. And of course, this resultant vector, because it is creating a right triangle, could easily be solved for with Pythagorean theorem. So the resultant vector would be 10 squared plus 4 squared is equal to d squared. So 10 squared is 100, 4 squared is 16, 116 is d squared, and from there we can find out the resultant of the object to be 10.8 kilometers. Now, because this is a vector, we can't just say that the displacement is 10.8 kilometers. We also have to get the angle in there. So we would have to determine what this angle is here and say that it is so many degrees north of east, or we could determine how many degrees east of north it is. Let's go ahead and determine how many degrees north of east it is. So theta then would be tan inverse of opposite over adjacent, which if we do that out, we find out that the angle of our displacement is 21.8 degrees north of east. So again, graphical method, you can, if they're straight lines, you draw them out and then add or subtract them. If they are at right angles to each other, you use a grid. Draw them to scale. So make sure that you are drawing them evenly spaced. So 10 kilometers is 2.5 times larger than the 4 kilometers one, and things like that. Because if you do draw them by scale, then you could use a ruler and simply measure the distance of your final resultant vector rather than having to do the math to figure it out. So you could use a ruler and a protractor to figure out your answer. And that's a perfectly acceptable way of doing things. If you don't draw them to scale, you should still draw them out with relative sizes the same so that you can have an understanding of what your answer is going to look like. Now, the last thing that we can do also is we may have vectors that are not at 90 degrees to each other and that they are not parallel to each other. And in fact, we may have more than two vectors that we need to look at. So when we are looking at those sorts of situations, the graphical method is really useful to us, and looking at making sure that we have drawn it in proportions again is important, because then we really get a good idea of what's happening. So for example, let's say that we had one vector, a velocity vector going that direction. We wanted to add it to a velocity vector going down. And then after we'd gone up to the upper right corner and then straight down, we turn back towards our home position. If we want to combine these, we can go ahead and still do the same thing for graphical method. And when we put them together, we put them together in what's called the tip to tail method. You can notice here, even from the very most basic part, we put the tip of one vector connected to the tail of the next, the tip to tail here in the center as well. As long as we connect vectors tip to tail, then our resultant vector is easily drawn from the tail of the very first vector to the tip of the very last vector. So in this third situation here, for example, I have V1 going diagonally up to the right. My V2, I start at the tip of my V1 and I go down. My V3, I start at the tip of my V2 and I go over. And then to create the resultant vector, I start where I started off here and I end at the tip of my last vector, and my resultant vector is there. So when we are combining vectors graphically, this particular method of doing so is called the tip to tail. Many students find this to be the easiest one to do. However, it is not necessarily the one you have to follow. Okay, so this is just one method of combining vectors. Another method is what's called the parallelogram method. And I will show you the parallelogram method using a couple of vectors from the third one here. So for the parallelogram method, rather than connecting the vectors from the head of one to the tail of the next, head of one to the tail of the next, you are going to be connecting the tails together. So on our last example, we had, for example, the 10 kilometers east, and then from the tip of that head, we went up 4 kilometers north. And remember, our resultant was from where we started to where we ended. The parallelogram method, however, we would start them all at the same point. So we would start the 10 kilometer vector, and then the 4 kilometer vector would start the same place. And now to find the resultant, rather than going from tip to tail, because we don't have any of that anymore, because they both start at the same point, we're going to finish off a parallelogram. And so what we do is we draw a parallel vector at the tip from the 10, and we draw a parallel vector from the 4. And we create a parallelogram. Our resultant vector then goes from the origin of where our vectors are out to the opposite corner of our parallelogram. Now, this vector and the vector that we did previously with tip to tail method should be identical. They should have the same angles here, and the resultant sizes should be the same. It may seem like tip to tail makes most sense, and for many people it does, and you'd want to use that all the time, but there are situations where drawing parallelograms is going to be make more sense for the physical situation that you're looking at. If you're talking about going on a trip, then the tip to tail method makes most sense. Parallelograms, again, the way it works is you have vectors start at the same place, so two vectors start at the same place. Then you draw the other two sides to make a parallelogram, and the resultant is from the start to the opposite corner. Super easy to see if they are at right angles with each other, but let's say for a moment that these vectors are not at right angles, like the other one that we had, where we had v1 going up to the upper right-hand corner and v2 going straight down. If we have that situation where v1 is like this, v2 is going straight down, we still want to draw a parallelogram. So to draw the parallelogram, we still need to first draw the vectors that are parallel to the two vectors that we have. So from the tip of v1, I would draw a line parallel to v2. And then from the tip of v2, I would draw a line parallel to v1. And then my resultant vector would go from where they start to the opposite corner. Now, in this particular case, I had a third vector going to the left. Once I have this resultant vector, I can then make another parallelogram with my first resultant vector and v3. So I have this resultant vector, and I have v3. And again, I make my parallelogram, and my final resultant vector is here. Again, going from where you start to the opposite corner. So parallelogram method can sometimes take longer than the tip to tail method, but the situation will determine which one makes it easier for you. One last thing that you want to remember is that if you are having a situation where you're trying to subtract vectors, subtracting is the same as adding a negative vector, so you can just flip it 180 degrees. So, in other words, let's stick with v1 plus v2 over here. This here that I circled is v1 plus v2, whatever my velocities are. But if it was written as v1 minus v2, then I would need to flip v2 and still go ahead and process this the same way. So my v1 would still stay in the same direction, but my v2 is now negative of what it was. So really keep this in mind as saying I want to add a negative v2. So rather than it going down, it would go up like this. And then I'd find the resultant vector that way. So subtracting vectors is the same as adding negatives, and that is the same as just flipping your original vector 180 degrees from its origin. Graphical method is an easy way to solve vectors, assuming that number one, you have specific values and angles for them, and number two, that you draw them to scale. If you draw them to scale using the same scaling size for all parts of your problem, then you can get the answer directly off the graph, off the picture. Otherwise, you can draw it with relative sizes and do the math to figure out your answer. Another way that you can do this, and this is the way that you will find some of the problems referring to motion and vectors in particular, and speed vectors in particular, velocity vectors in particular in this course, is by using the unit vectors. When you are using unit vectors, you're going to be adding by components. So in other words, the first thing we want to think about is this is typically when we start drawing vectors in 3 dimensions, 2 and 3 dimensions. Most of the time we'll stick with 2 dimensions though. So similarly to solving graphically, you start here by drawing a diagram of the vectors and showing how they would add graphically. But this time the diagram does not have to be as accurate as when solving graphically. After drawing, you're going to choose your x and y axes. You're going to resolve the vectors into their components, and using the unit vectors as a guide, calculate each component using sines and cosines. Once you have done that, you then add the components in each direction to find the length and direction of the resultant vectors using Pythagorean theorem and some of your basic trig functions. So keeping in mind, what is a unit vector? Well, if we have a 3-dimensional grid system here, right? We have y going up, x going over, and z coming out of the board. Then our unit vectors are I in the x direction, j is the unit vector in the y direction, and k, of course, is the unit vector in the z direction. So if I want to graph a velocity vector that is in 3 dimensions, I would need to be able to write my velocity vector in terms of my x component in the I direction, my y component in the j direction, and my z component in the k direction. So once you have separated out your velocity vector into its x, y, and z components, then you add up all of your vectors in the I direction, add up all your vectors in the j direction, add up all the vectors in the k direction, and then use Pythagorean theorem to recombine them and to find your theta of your resultant. Not all of the problems we do will be using unit vectors, but some of them do, and it's a good idea to keep this diagram in mind and to remember how you go from one to the other. All right, so now let's look at what does this mean when we are talking about vector kinematics and talking about adding and looking for instantaneous velocities and instantaneous accelerations versus average velocities and average accelerations. In 2 or 3 dimensions, displacement is a vector. And when we have displacement being a vector, we have to keep in mind that our delta r is going to be r2 minus r1. So we may have gone from point 1 to point 2, but to find our displacement vector, we would need to know the displacement vector from the origin to point 1, and then from the origin to point 2, subtract those two, and we get the resultant vector. Now, please be aware that this is a subtraction, and the subtraction is why we can just simply draw the resultant vector between the two heads of these position vectors. If we were adding them, they would have to be rearranged, and we would have to do the parallelogram method or the tip to tail method. But this R1 is adding its opposite. So R1 really goes the opposite direction. So it is tip to tail, and we're good there. As delta t and delta r become smaller and smaller, the average velocity approaches the instantaneous velocity. So here, displacement is a vector. This displacement leads us to our velocity if we were to plot this with time. So if we go ahead and plot R1 and R2 with time, then as our time gets smaller and smaller, the difference between these two will get smaller and smaller. And the average velocity that we're looking at will become the instantaneous velocity, because remember, velocity is the limit as delta t goes to 0 of delta r over delta t, or dr dt. Once we get to that point, then you really need to think about, well, if we're really approaching the instantaneous velocity, then we're going to be able to get the instantaneous acceleration, and the instantaneous acceleration is going to be based on velocity vectors. So I can use these displacement vectors, which give me a velocity vector here, to figure out my acceleration. And the instantaneous acceleration is in the direction of delta v being in the direction of v2 minus v1. So again, we're going to go back to our first picture. We have our displacement vectors. R2 minus R1 would give us our displacement here. As that displacement changes, we can look at our v1 and our v2, the velocities at point p1 and point p2. Then we can say, okay, there's definitely change going on between them. So how much change was there? We can subtract the two and get our delta v. That difference in velocity per time we already know is acceleration. So we can get our acceleration by thinking of just subtracting our velocity vectors, or saying that we can subtract our velocity vectors in smaller and smaller time intervals and eventually get to the point where our instantaneous acceleration is dv dt. Again, the reason that I'm showing you this in a graphical format as opposed to the equations that we did in the last video is because oftentimes it's easier in calculus to look at it in terms of the picture rather than the equation. Now, we can take all of this information here with the vector kinematics and looking how you can go from displacement to velocity to acceleration, and we can use the unit vectors and write velocity and acceleration as the following equations. Our velocity we know is dr dt, which, if we are working in more than one dimension, needs to be broken down into the component displacements. So it's really dx dt in the I direction plus dy dt in the j direction plus dz dt in the k direction. So we can take our velocities and write them in terms of the derivatives of displacements in each of the different unit vector directions. And from there, we can take the next step and say, well, then acceleration, which we know is dv dt, must be the derivative of all of these, which would then say that it is dvx dt in the I plus dvy dt in the j plus dvz dt in the k. Now you keep these equations in mind, and whether you're dealing with 1, 2, or 3 dimensions, you can still use these as your basis equations. Because if you're dealing in 1 dimension, then you would just have the first term. 2 dimensions, you'd have the first 2 terms, and then of course 3 dimensions, you would use all of them. So now let's get to solving a relative velocity problem. in 2 dimensions. When we label velocity vectors in 2 dimensions, the first subscript refers to the object that we are talking about, and the second subscript refers to the reference frame in which it has that velocity. So here, v of ws, for example, refers to the velocity of the water in the shore reference frame, which means that the VBS is the velocity of the boat in the shore reference frame, and VBW is the velocity of the boat in the waters frame. We can combine these based on how it's drawn to know that if we add the velocity of the water in the shores frame plus the velocity of the boat in the waters frame, we will find out what the velocity of the boat is in the shores framework. In other words, according to somebody standing on the shore, what is the boat actually doing? So again, we can say that VBS is equal to VBW plus VWS, because remember, we want to go tip to tail, and here's a tip to tail situation, so VBS is our resultant velocity. It's really important that you set up this equation correctly. Even if you draw the picture correctly, if you set up this equation correctly, incorrectly rather, and have the equal sign in the wrong spot, your answers are going to not make sense. So let's say in this example, the boat's speed in still water is 1.85 meters per second. And the boat with respect to water then is 1.85 meters per second. If the boat is to travel directly across the river, whose current has a speed of 1.2 meters per second, at what upstream angle, must the boat head? So again, the current of the water is 1.2 meters per second, so that is this, 1.2 meters per second. And the question is, what is theta? Well, according to this diagram here, our theta could be found by knowing the tangent. So tan theta, remember, is VWS over VBW. So theta equals tan inverse of 1.20 over 1.85, which gives us an angle of 32.97 degrees upstream. Or you could say northeast. The reason that we are going to 32.97 degrees to the hundredths place is because if you take a look at the values I gave you, the speed for the boat with respect to the water is 1.85, and the river current actually should have a 0 on that, so it would be 1.20 meters per second. These problems are often tricky because it's really easy to set up the diagram incorrectly, and then that makes this first equation here incorrect. So please keep that in mind and draw out your diagram and label your vectors carefully before you move on from there. Let's do another one. Same boat, same river, but rather than having the boat try to cross directly across the river, we're going to have the boat just head across the river with the current and see what happens. So in this particular case, here's our river. We have our boat, and it's going to go across with a velocity of BW, which will be the same, 1.85 meters per second. It's the same river, so the river will still have a velocity of the water with respect to the shore of 1.20 meters per second. But now the question is, what is the velocity of the boat relative to the shore? If it starts out straight across, what's the current going to do to it, essentially? So now we want to know this. What is the velocity of the boat relative to the shore? Okay, well, we're going to look at it the same way as we did before. We are looking for the velocity of the boat relative to the shore. This is a right triangle, so we're going to use Pythagorean theorem, and we're going to find out that 1.85 squared plus 1.20 squared is equal to our VBS squared. We solve this, and VBS is 2.21 meters per second. The question then becomes, because we want the velocity, this is its speed, but we need to know its direction, so we have to find out what is the angle that the boat ends up going. And keep in mind the river is going in this direction, so the angle is going to be downstream. We can determine this the same way as we did on the last problem. It's still going to be another tangent. So theta is again equal to tan inverse of 1.20 over 1.85. We already know that from the last screen that this is 32.97 degrees. But again, this time it will be downstream. So the boat will have a speed relative to the shore of 2.21 meters per second at an angle of 32.97 degrees downstream. If the river is 110 meters wide, how long will it take for the boat to get across the river, and how far downstream will it end up? The travel time is going to be determined by the time it takes to go directly across. So it's going to be determined by this speed VBW. So keeping in mind that VBW will be d over t, and d being the width of our river, it will be, our time then will be 110 over 1.85, and that is 59.5 seconds. So it'll take almost a minute for the river to get across, for the boat to get across our river. And during that time, the boat is carried downstream a certain amount of distance, and that distance is going to be based on the velocity of the water, the current speed based on relative to the shore. So then we want to find out the distance x, which would be VWS times t. So 1.20 times 59.5. And we find out that the boat would end up 71.4 meters downshore from where it launched. Now, depending on what's happening on the other shore, that may be a good thing or that may be a bad thing. But you can see how slightly rearranging the two pictures in this setup is going to give you different results in terms of how fast the boat's going and where you're going to end up. Even though the angle remains the same, the other information changes. So the key to relative velocity problems is to make sure that you understand how all of the objects and directions interact with each other, and to make accurately labeled diagrams to go with the situation. That's it for now for vector kinematics and relative velocity. So bye for now.